The next speaker is Professor Sam Kono. He is a professor of the Tokyo Tech and a graduate from Kyoto University. And he also received a PhD from University of Illinois at Champaign, Alabama. His research interests cover seismic assessment, seismic retrofit, performance-based design, damage control system, precast and pre-stressed concrete, and high-performance concrete. Please, Professor Kono.
Okay. Thank you very much, Johanna-san. Okay. My name is Sam Kono from the Tokyo Tech, and I'm very glad to come here and make a presentation. Oh, like this. And then this is some kind of effort we are trying to do, especially in the building structures. Okay. And then the seismic design for buildings made in Japan, what's happening after the 81. We make a big revision in 81. The revision up to that point, this one, allowable stress design. Okay. And so until the 81, we are designing the building for the intermediate earthquake, and then using the allowable stress, and then stopped it. And so we don't know how it's going to fail under the large earthquakes. But 68, 78, lots of earthquake, and then the building collapsed, and people started to worry. Why? Because we are not designing for the ultimate conditions. And so the Japanese society decided, we need to design for the ultimate conditions, for the large earthquake. And so only for the superstructures or above the ground, we started to design for this ultimate condition. And we check the lateral load carrying capacity of the building. Okay? And then that time, we didn't do anything for the ground or foundation. And so piles, foundation beams, we didn't see, or people didn't see any big damage. And so they decided, we don't do anything about the foundations. So there's no requirement for the second level design at that time. Since then, it's kept the same. Although we started to see some damage, and then, probably it's time to design for the large earthquake, even for the foundations. And then this is Kobe earthquake. And then after those 81 earthquake, we didn't see very much like a real collapse. And then if you follow the new design code, and then is it perfect? It's not perfect. For example, this like even if you follow the new design code, the new means 81 code, and then we still have the damage for the soft storage. And if you have a large like shear wall in the backside of the building, for example, and then there's a torsional effect, and still you have a damage to these columns because of the enforced displacement. And then also this is from the Kumamoto-san sitting there. And then this is 81 is the year of the Earth, those new codes. After that one, we didn't see very much like a collapse of severe damage to the buildings. But before that one, you see the really large like a collapse, the severe damage is happening. So we are saying, that's important to see the assessment of the buildings for the seismicity and also the seismic retrofit. And then the Tohoku earthquake, like 2011, and tsunami is one of the big things. But for the building side, due to the shaking, what we are going to see is this is like a gymnasium of the school. People are using those buildings for the evacuations. And so if you cannot use your own residential buildings, people go to these places, gymnasium, and then spend the time. But if you have a damage like this one, everything is shut down, and you cannot use those places as a refugee camp. That's really sad. And so this is one of the big things. And then these non-structural walls, especially. So until 95 or even 2000. And then the structural engineers, professor saying, oh, your building is quite safe. Nothing bad. It's okay. Because this is non-structural. But people started to feel, no, it's not quite right. We cannot live. With this big damage, and then you cannot use the building. And so people started to feel, oh, probably the safety is not the only issue. And that's happening also in the States or New Zealand, the same way, okay? Resiliency is one of the big issues. And so those are the things. And then the third one here is the foundation, especially the piles. And then some people feel or know those piles are damaged, even in 95 earthquake, but people didn't see, or I didn't even see them because it's not on the, we are not people, we are not seeing. And then the media doesn't know, professor doesn't know, unless the building is really like a tilting. Okay. But for the superstructure is good and something is bad, and so they dig the ground and they found out, oh, it failed like this one. And then for people working on these like foundations or soils, they knew from the 95, oh, the piles are getting damaged. Why? Why? Because we are not designing. Okay? And so here the safety is still the most critical issues. Even for Kumamoto, 2011, like Tohoku, 95, Kobe. It's really, like still the safety is big issues. But people are seeing, oh, resiliency. Okay? And so the new code is, our new code is like 81 code. They are securing your building is safe, no collapse. But they are not assuring like resiliency at all. That's what people are seeing these days. But that's probably not only in Japan, but which is happening outside of Japan too. And then just example for the 2011 Kumamoto earthquake. And then what you're seeing is these buildings. And these buildings, after earthquake, the superstructure is safe, but it's kind of tilted. And then people wonder what happened. So they dug out this foundation and then found out, oh, the pile is really damaged. Okay? And then so it's time. It's time to work on the pile for the large earthquake. And those are the really big motivations. And then what piles we are using, like timber, this is very old. Okay? And also steel. And the steel piles are mainly used for the bridges or civil type of thing. And we are not using very many things for the building structures. And then what do we use for the building structures? Mainly we have, the first one is precast concrete piles. We make this in the centrifuge. And so it's a spun concrete. And then they started these things for the like a 60 megapascal, 70 megapascal concrete. But these days, the main product is 105 megapascal or 125 megapascal. And then a few of them is this one is pre-stressed high-strength concrete pile. And then if you add the mild steel in the longitudinal direction, it's what we call PRC, pre-stressed reinforced concrete piles. And then there's a CFSD pile as well. And this is hollow. Everything is hollow because it's spun concrete in the centrifugal fabrication. And so this is one of the big things. Probably you don't see, as far as I know, I don't see them in States or Europe. But we use it here in Japan as well as Taiwan, probably in China. Because especially this PHC's price is low. And so for the building up to the 10 stories, probably the constructors or designers want to use this PHC because of the price. Okay. And then what's going to happen for the large scale or the high-rise building? They use the reinforced concrete piles or CFSD piles. And so this CFSD piles, for example, this red one is the shell, okay? And then the size is, it says like 700 mil to 2.5 meter. That's very large. And then but the thickness of the steel is like a 12 mil or 60 mil. And that makes D/T ratio, that is the diameter to thickness ratio of the steel, is 100 to 200. That's very large. So that means like, this is really skinny, like a shell is around the concrete. There's a lot of study on the CFSD column, and then those D/T ratio is 30 to 50. And so you have a really large, thick, like a steel, and then steel can hold the compression a lot. But for these skinny things, you cannot expect the development of the full capacity, plastic capacity. Okay. And then this is example of the spun concrete pipe. And then there's like a PHC, PRC, CFSD. Okay. And then here, the really typical one is 105 megapascal, hollow section. D/T is around 60 to 100. And then the diameter itself is 300 to 1200 mil. And so they are used for the up to 10-story building. Okay. And then for the PHC, you don't see any shear rebars. These like spirals are for the assemblage purpose. PRC, they add longitudinal as well as spirals. And then you can expect a little bit like a shear confining effect. And then CFSD, there's no rebars at all. And they never tested the pile under the large, like axial load. And so this horizontal one is axial load ratio, probably. This is the axial load itself. And then the vertical one is moment. And then the pile companies tested about this range. But we found out those like piles are used under the larger axial load. Like axial load ratio is 0.4, 0.45. That's still common under the large earthquake. And also they never tested the pile under the intention. And so we decided, oh, probably we need to do it. And this is the test setup. And only, this is like simply supported 4-point bend test. But to apply the load, we put this like a frame. And so this is only for the frame to apply the axial load horizontally. And then the hydraulic jack is hidden in here. And the total is 2,000 tons in axial load. Okay. First one is PHC, and then this one is under tension. Yeah, of course, like it's ductile. And then this is under the axial load ratio 0.42. And then up to this point, and then it's really explosive. This is the first one. Under the tension, it's ductile, it's okay. And then I used to have a video, but I don't have it. It explodes. It's really scary. Okay. And then usually we go and take a look, and then the students draw the line, and then those like industry people said, never do it. It explodes, and they really exploded. And then the PRC, why the PRC? Because you add the mile rebars, and then you increase the load capacity a little bit, and also probably the ductility. That's what the people expected. And then under this, again, like a tensile axial load is ductile. Or up to like 15%, 20%, its behavior is okay. But like if you apply the axial load ratio like 40%, again, it's exploded. And so those shear rebars or mile rebars doesn't work at all. Its behavior is about the same with PHC, PRC. Both of them are very, very like brittle. And then same, and I don't have a video, sorry. And then the CFSD, the PHC PRC, they use mainly at the very deep at the soil. And then if you have a large moment at the top, the designers usually use this like CFSD pipe on the top of them by splicing the pipe. Okay. And so they're kind of expecting the capacity as well as some deformation capacity. Yeah, it's much better than the PHC, PRC. This is 10% of actual load ratio. This is ductile, and I have a dissipate large amount of energy. This one, what happened? It buckles, and then the concrete inside probably crushed at the same time. And so it's not as ductile as you think. Okay, and then until now, people are designing up to this point, like allows this design. But even if you apply the ultimate capacities, can you make sure like it's ductile after that one? But no, it's not as ductile because DO2 ratio is 60 to 100, and it's hollow and the high strength and no rebars, and then once it crushed, it drops. And so the behavior is not as good as that. This is happening under even like 18% of the actual load ratio. So it's not very high. We also tested 25% or 30% of the actual load ratio, and then the behavior is more brittle. Yeah, this like buckling happens. And then once it's buckled, this portion is very brittle, and then the next you pull it, and then it's fractured. Yeah, so this is moment capacity. For the moment capacity, if you use this cal is like a plane section being plane, and then the perfect bond between concrete and steel, bond, those like PT tendon, then you can predict it's okay. Okay, and then we assuming, I think we are assuming like 0.3% of the ultimate conditions, and then yes, under that condition, the capacity can be predicted kind of safely. Although like see that scatter is large, probably because of the shrinkage. Because after the centrifuge, we put them into the autoclave, and then the probably shrinkage around the rebars is large, and so the scatter of this PRC is much larger than PHC. And this is for the precast CFSD, so it's hollow. Okay, we are using the same method for the sectional analysis by limiting the strain of the concrete, and then the ultimate condition is we are using right now is 0.4%. And then if you apply a higher actual load, then these things is below 1. Now that's kind of scary because we are expecting much better behavior for the CFSD. And so we are limiting the ultimate this strain to the 0.3 under the large axial force. Large axial force plus like if DC over TC is not the same thing with thickness to the radius of the thickness ratio for the concrete part. Okay. And so those numbers are large means it's thinner. Again, like it's unstable, and so that you cannot attain this capacity. And so we changed by limiting these things. Okay. We are probably supposed to consider those like thickness rate, thickness effect explicitly. Time. How much? And then this one is like a casting plate CFSD. Again, like a D over T ratio is 100 to 200. Their main product is like 140 to 160. And then somebody checked the design condition, and then they see this like unreinforced like CFSD is used under the up to 40% of the actual load ratio. If you put the longer rebars, and then they're using up to like 50%, that's very, very large. And then again, like if you applied axial load. This is like a 1.2 meter diameter, so 4 feet, very large. And then we applied almost like a 2,000 ton axial load. This is fabrication. And then under the compression, it buckled from ENSC. This is buckled. And after that one, you press it and then it's extended, it fractures like this one. And this zigzag is due to the fabrication. They are using the inside of the ribs for the shear key. Okay. And these things with stress concentration happens, and so the fracture happens like this much. Okay. So even for the CFST, like up to the failure, it's fine, but the failure happens the negative side. Because it's compressed, this is compression, and then it's that kind of ductile, even after 40% of actual ratio. And then if you pull it, and then it fractures. Okay, and so those are something that people are not expecting for the casting plate CFST piles. People assume in both directions it's very ductile and countable, but probably it's not. And then again, like you use the texture analysis. Yeah, it's okay. Rather, like many of them we are kind of undershooting because epsilon CU is limited to 0.3. That is very like a small. In the test, the maximum is attained around like a 0.45 or 50.5% of the strain at the compression fiber. But we are limiting to the 0.3, and so for sure, like it's kind of conservative. And probably the next phase is we need to consider the deformation. How much the deformation capacity we have is a big issue. And this is again from like Komuno-san and Taisei Corporation provided us these things. This is reinforced concrete piles applied like a 40% or 50% of actual load, and then the cyclic testing, and then this is 0.5, and it's really dropped. And so they decided, oh, probably we want to go to the 0.6, but instead of going to 0.6, they decided to do the 0.4. Even for 0.4, like a degradation is so quick. And then partly because of the crushing and also these vertical cracking due to the large axial force plus like a shear. And so it's kind of easy problem because people have worked on the columns, for example, and the CFST, there are lots of like test results, but not for this like a particular one, because these are a little bit different from the columns. As I said, like a thinner or high strength, it's hollow, or sometimes like this CFST V/T ratio is so large. And so you can expect some similar behavior, but like existing code equation does not cover the behavior of these things. And so you need to test it first, see the behavior and the failure mode, and then formulate them. Those are very important issues. The same for the RC piles. And then this is just a summary of the pile itself. And then there's also shear problem, although probably I'm just skipping them. And the failure mode is different. And then the pile is not the only issue. This is pile. And then this is simulating, this is beam, and this is supposed to be column. And then this is pile cap behavior is another issue. And so there's a shear failure as well as some kind of a flexure failure at the pile head. And then which portion you are going to make a plastic hint is a big issue. Okay, time. Okay. And then those pile cap, and there is some like a revision made in the AIJ code, but we are still working on it. Okay. This is some area. Okay, thank you very much.
Excuse me, a quick question.
Okay.
So do you think that the concrete piles failure Was there any lateral spreading that happened in the soil and that might have increased the unbraced length of the pier and that caused failure like you have shown in pictures?
Sorry, I didn't understand. Sorry, I didn't understand the question.
So did you notice any kind of a lateral spreading of soil?
Soil conditions.
Yeah. So the way the drill piers are failed, they fail as if there's a long unbraced length of the column, right? So was there any, when the geotech investigated after the seismic, did they notice any kind of lateral spread?
Some of the building, yes, due to the side spread of those like a soil condition, the pile failed, but not all of them. Not all of them. And the couple of buildings which had the damage of the pile, not due to the side flow of the soil, but just due to the probably shaking of things. Thank you very much for asking.
Is there any chance for questions?
Okay,
Sorry, thank you very much. Very quickly. About your building codes, as it was clear to me, you are saying it's going to change. But it's going to change in which direction? In the sense that you are asking some activity for the piles, or you are designing the foundation with overstrength. So this is quite crucial.
Right now, for like under building is lower than 60 meters, and then you try to design for the foundation structures for the large earthquake. And we said design for the large earthquake. And then probably in the future, we need to design like which portion have like a plastic hinge. Right now, you fix the foundation and then do the pushover analysis or something, and then you.
But you do it with overstrength or not? Because if you do with overstrength, then you don't need a pin.
Like we started to think about like a whole building, including the foundations need to be included for the analysis. But it's a big discussion because of the soil conditions. And soil people said, no, your spring is wrong. And they use this spring for the static condition, they use this one for the dynamic condition, but nobody knows like, which spring is right. And so once you give it the spring property or something, and then the whole building can be analyzed with the foundations. And then probably you can make a more like an optimum or proper like a collapse mechanism.
Okay.
That's possible.
Thank
Thank you.
Thank you. Time is up. Thank you. This is a small gift.
Thank you very much.